Quantum computing has been a buzzword in the tech world for years now. Major companies including Google, IBM, and Microsoft are investing billions of dollars into research, and we have seen a lot of headlines about quantum supremacy, where quantum computer outperforms and solves a problem in seconds that would take the world's fastest supercomputer more than 50 years to solve. But with all this hype, it's very easy to get lost in unrealistic expectations. So let's step back and see what quantum computers actually promise to do, how much of the hype is true, how much is overblown. Let's break it down. Before we jump into how it works, let's compare it to something we all know and use, our traditional computers. Our traditional computers run on bits, which are like little switches that can be either a 0 or a 1. That's how every task in our computer is processed, from opening an app to playing a video. But quantum computers use qubits, that is quantum bits. Qubits can be 0, 1, or both at the same time because of a concept called superposition. For example, imagine you are flipping a coin. In a classic computer, the coin is either heads or tails, but in a quantum computer, it's like a coin is spinning in midair, representing both heads and tails until it lands. This property lets quantum computer handle much more complex calculations simultaneously. Another key concept is entanglement. Think of it like two dice that are linked. If you roll one dice and it shows a 6, the other dice will automatically show a 6 as well, no matter how far apart they are. This connection is what we call quantum entanglement, where the state of one qubit directly affects the other, no matter how far apart they are. These two properties, superposition and entanglement, allow quantum computers to process exponentially more information than a classic computer. But here is the catch. Quantum computers are not better in every way. They excel in specific tasks but can be useless for many others, where traditional computers are perfectly efficient. To understand this, let's dive into the math behind quantum computing. It's simple, just follow along. Starting with qubit, mathematically we represent a qubit in superposition as the combination of probabilities of a qubit being in a state of 0 or 1. Traditional computers use binary logic gates like AND, OR, and NOT to perform operations on bits, which can only be in one of the two states, 0 or 1. But in a quantum computer, to manipulate qubits, we use quantum gates. When a qubit passes through this gate, it transitions from a defined state into superposition. Now, when we have multiple qubits in superposition, they can become entangled, creating a powerful connection between their states. Think of it like this. If we have two qubits, each in superposition, their combined state can reflect a mixture of all possible outcomes. For example, if both qubits are put into a superposition, we can represent them in their joint state. In this state, measuring one qubit instantly reveals the state of the other, regardless of the distance separating them. This unique relationship allows quantum computer to perform calculations that leverage the interconnectedness of qubits, making computers more efficient, exploring multiple outcomes at the same time. So why does all this matter? The unique properties of qubits combined with superposition and entanglement allow quantum computers to excel at solving highly complex problems and computationally intensive problems. For example, in quantum chemistry, they can simulate molecular interactions more efficiently than traditional computers. In logistics, it can optimize delivery routes for countless trucks, evaluating numerous options in parallel. And in AI, it can enhance machine learning tasks, particularly in training the model. AI depends heavily on optimization and probabilistic calculations, which quantum computers are uniquely suited to handle. In machine learning, training deep learning models involve adjusting vast number of parameters to minimize errors. Quantum computers could accelerate this process, potentially allowing us to train AI models faster and more efficiently. It could also help in searching through large data sets or optimizing complex functions. However, quantum computers won't be useful for everything. For everyday tasks like browsing the web, editing documents, or playing video games, classical computers are far more efficient. Quantum computers are like the specialized tools, highly effective for specific problems but not meant to replace traditional computers for general tasks. Even with AI, quantum computing is still in its early stage and is not advanced enough yet to fully replace classical systems. And the integration of quantum computing into AI is still experimental. So the takeaway here is that quantum computing excels in solving specific complex problems, especially those related to optimization, simulation, and certain AI tasks. But it's not a one-size-fits-all solution. Traditional computers will still be far more efficient for the majority of tasks. And for now, quantum computing will remain a complementary tool in our technological toolbox. That's all for this video. If you like this video, hit the like button and subscribe for more interesting videos coming up.